Hello, 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 hello. So we've done some preliminary material in chapter 5, and now we're kind of settling down to actually talking about the kind of core material of the chapter, which is complexity classes. So what we're going to talk about today, although it's short, it's only 3 slides, it's in fact the most important complexity class. And so I'm going to spend a few minutes justifying it or trying to explain why we give it so much attention. Okay, so the complexity class is called P. You remember that a complexity class is a collection of languages. We're pretty much identifying the problem and the language together. We're going to focus on language decision problems, and so we consider that the collection of problems and the collection of languages are pretty much the same thing. Okay, so a language decision problem is a member of the class P if there's an algorithm for that language decision problem that on a deterministic Turing machine runs in polynomial time. Okay, so the class P is the one that the P stands for polynomial time. The class P is the one that we give the most attention to, and it's the one that you have an awful lot of experience with. So here are some examples of decision problems that are in P, language decision problems. So I'm going to describe the language. So the very first one is intended to be just the most straightforward and simple thing you can think. It's a triple ABC, and all you're supposed to do is recognize that A plus B adds to C. Do that in polynomial time. If I give you a triple, 7, 19, 31, is A plus B equal to C, yes or no? I think you can do that in polynomial time. Okay, the language of sorted strings. So that is to say I'm going to give you a string, might contain thousands of characters. I'm going to give you a string. You've got to answer whether that string is in alphabetical order. Now here I have the string being just the letters lowercase a through z. So it seems like an awful straightforward problem, but you can imagine a more complicated version of that where you're just trying to make sure that the input is in order. Think you can do that in polynomial time? I'm not telling you to put it in alphabetical order. I'm just telling you to recognize if it is in polynomial order. Excuse me, if it is in alphabetical order. Okay, so again, trying to impress on you that these are problems that you know how to do. The language of correct matrix multiplications. So if I give you 3 matrices, A, B, C, is it the case that A times B equals C? And a person would say, well, how could that go wrong? Just like the 2 previous ones. How could that go wrong? Well, A, B, and C may be very big, so it could take a long time. Okay, but don't get confused here. It's not, we're not saying that these operations don't take a long time. We're saying that they are polynomial in the size of the input. Okay, so if you give me big A, B's, and C's, of course it could take a long time. If you give me A with 100 million rows and 100 million columns, et cetera, of course it could take a long time. But polynomial time in the size of the input? Yeah, sure, yeah. Some kind of n cubed like time in the size of the input. That's what I think. Okay, what about the language of primes? You're just going to give me a sequence of ones. Say, 217 ones is 217 prime. So again, polynomial. I think you can check for primality in polynomial time. And then for the language of reachable nodes with 5 neighbors. So we're going to look at a graph here. We're going to look at a graph here, G, and ask, does it have exactly 5 neighbors? Can you check that in polynomial time? And again, polynomial time in the input G. So if G is a very big graph, then you're polynomial in a bigger number, but it's a question of polynomial in the input size. Not absolutely fast or slow, but fast or slow relative to the input size. Okay, forgive me, I've seen folks get confused about that before. So we're looking at problems that are in some sense easy. Sense of easy is that you can solve them in a time that's polynomial in the input size. So I drew a picture. It's not a very good picture. So I drew a picture. I drew all of the problems here. I drew all of the problems here. All possible languages. So this is all languages. And again, I'm not going to distinguish too much between between the language decision problem and the language. So this is all languages, and of course there are some languages up here and some languages down here. What does up and down mean? Well, this means they are problems that take a long time to solve. The fastest algorithm for this problem takes a long time. The fastest algorithm for this problem down here at the bottom doesn't take very long at all. And what I've drawn here, and you can only do so much with a sketch, but what I've drawn here, these are all the problems whose solution time, where there is an algorithm for them, whose solution time is polynomial. You notice that there's some shading here, darker to lighter, and that's just simply trying to convey that you have problems that are big O of n, big O of n squared, big O of n cubed, big O of n to the fourth, etc. And so it kind of fades off into the distance. But still, these are in some sense the fast problems. You can solve them in polynomial time, and Cobham's thesis is that these are the fast problems. Okay? Okay. So the problems for which there exists an algorithm that you can that returns quickly, returns in a polynomial time on the input. Okay. So just a brief comment about the effect of the model of computation. The previous slide talks about being polynomial in the input size, and a person might say, well, doesn't that depend on the model of computation? I mean, look, Turing machines, we avoided programming in them because they are a pain in the neck, and it strikes me that they're very slow. Turns out that Turing machines are slower than a lot more familiar models like the random access model, but not that much slower. So close analysis shows that means that you actually get down and do the details. Close analysis shows that Turing machines are typically slower than other natural models, like the random access machine model, by a factor of n squared or n cubed. So if you have an algorithm that, for example, is big O of n on another model, maybe on a Turing machine, maybe it's big O of n to the fourth. So in that sense, Turing machines are slow. But they're all still in P. So a problem that falls in P with, say, random access, the RAM model, the random access machines, it is still in P if Turing machines are your preferred model. So the model of computation there is not causing trouble for the definition of P. Okay. But one of the exciting things about this course is that sometimes, you wake up in the morning, you get your coffee, you sit down, and you read what's going on, and things are different than they were yesterday. So this is an example, because what's happening now, very exciting, is that there is a possible counterexample to the contention about there being an at most polynomial time delay between different models. That Turing machine, the random access model, different models that idealize physically realizable devices. Under the quantum computing model, there are several problems that have polynomial time solutions. I'll just mention integer factorization as an example of a problem. Under this model, there are several problems with polynomial time solutions that we don't know of a polynomial time solution for a Turing machine. So there's a lot of hedges there, but nonetheless, it appears, best educated guess is, it appears that quantum model changes the paragraph right above. It appears that quantum computing model can do some things can turn some jobs from non-polytime into polytime. It appears. Now, a person could say, well, quantum computing, kind of exotic stuff. It's not clear to me that it idealizes a physically realizable device, because it's not clear to me that quantum computers are physically realizable devices. Yes, that's a very good point. It is, at this point, we don't have them in our pockets. Fair point. Nonetheless, there at least appears to be a possible counterexample, there appears to be a monkey wrench here in the works for what it says on this slide. So rather than just continue on as though nothing had changed, in fact, it might be that things have changed. So I'm mentioning it to you. But you come down, you get your coffee, you look and say, whoa, the world is different today. Very exciting. Okay, last slide. I mentioned this was a three slide topic, very important topic, but a short one. So why P? So of course, one reason for P is Cobham's thesis, because we're thinking about problems that we think of as tractable. Okay, fair enough. So that's a very important reason, probably the most important reason. But two more points. So as we just mentioned, if a problem is in P based on any model like Turing machines or integer RAM or scheme programs or JavaScript or whatever is your favorite language, then it's in P for all of them. That is to say, if you take down an algorithms book off the shelf and you find that there is an algorithm that runs in polynomial time on what is your book called Algorithms in C, well then that algorithm runs in polynomial time on a Turing machine when suitably modified. So P is a class that in some sense contains all of these problems that we are used to solving on physically realizable devices. So it's an important class. It's a touchstone class. One more reason, a more mathematical technical reason. We'd like to think that if we have two things that are easy to compute and we perform a simple combination of them, then that's also easy to compute. So said more precisely, where we take easy to compute, meaning in P. Said more precisely, if you fix two total functions, f and g, and you look at these two language decision problems, L sub f and L sub g, L sub f is just simply pairs of input-output for f, and you got to cast those into bit strings. That's all. L sub g is input-output for g. So I've expressed these functions somehow as languages. Okay. Now with that restatement, then P is closed under function addition. P is closed under function scalar multiplication by an integer. That is to say, if you know L sub f, do you know L sub 3f? Yeah, that's polynomial type problem. It's closed under subtraction, function subtraction. It's closed under function multiplication, closed under function composition, closed under language concatenation, closed under Kleene star. It is the smallest non-trivial class with all of those appealing properties. So P is a natural class to talk about. It would be not bizarre, but at least a little bit of a head scratcher if somebody said, I want to talk about problems that can be solved in n cubed time, and not n to the 3.00001. That's no good for me. You'd be like, okay, why? But if you say I want to look at polytime, then you don't have this kind of arbitrary ceiling. So that makes polynomial time in some ways a very natural class. Okay, great.